Welcome to this explainer. Okay, today we're diving headfirst into a really wild math world for something called the exponent adventure. We're going to explore this totally mind-bending concept, how seemingly tiny, unassuming numbers gain absolute superpowers just by multiplying. If you've ever wondered how sequences can scale so incredibly fast that human intuition just totally fails, or how this very math protects your bank account and measures the universe, well, you're in the right place. Let's get started. So let's lay out exactly what exponents are. It's not just some basic math suggestion, right? It's an incredibly powerful operation representing repeated multiplication of a single number. We aren't just taking two numbers and multiplying them once. Oh no, we're taking one number and multiplying it by itself over and over and over again. Understanding this core mechanism, repeated multiplication, is the absolute key to everything we are going to unpack today. Now, to really get why exponents are basically a superpower, we actually need to look at what they aren't. Imagine you want to build a ladder all the way to the moon, and you're going to build it step by step. Let's say every step on this ladder is exactly 20 centimeters high. You take one step, you're up 20 centimeters. Two steps, you add another 20, so you're at 40 centimeters. Three steps, 60. You get the idea. This is what we call linear growth. You are just adding the exact same amount repeatedly. It's steady, it's completely predictable, and honestly, it's agonizingly slow. Just how slow is linear growth? Well, the moon is roughly 384,000 kilometers away from Earth. If we strictly rely on that linear growth model, adding just 20 centimeters of height with every single step, the math is just exhausting. It would take you roughly 1.9 billion steps just to get there. That is the ultimate limitation of repeated addition. Sure, it gets you there eventually, but the journey takes absolutely forever. Okay, let's flip the script. Toss the ladder and grab a simple, ultra-thin piece of paper. Every single time we fold this paper in half, the number of layers doubles. One fold gives us 2 layers. 2 folds give us 2 times 2, which is 4 layers. 3 folds give us 2 times 2 times 2, which is 8 layers. 4 folds get us to 16. Now, instead of writing out all those 2's again and again, we just use an exponent. We'd write 2 to the power of 4. So what if you folded this paper 46 times? The number of layers would be 2 to the power of 46. And here is the absolute mind-blowing part. That stack of paper would literally be thick enough to reach all the way to the moon. That right there is the sheer power of exponential growth. It starts off super slow, but man, does it skyrocket. This contrast really drives home the difference we're talking about. On one hand, you have the ladder, growing by adding a steady 20 centimeters each time. On the other, the folded paper, growing by doubling or multiplying. Linear growth is 20 plus 20 plus 20. Exponential growth is 2 times 2 times 2. The big takeaway here is that while addition plods along steadily, multiplication is explosive. It grows so fast that our human brains honestly have a hard time anticipating the result. To prove just how tricky this exponential pacing can be, let's try a classic riddle. Imagine a magical pond, and it starts with just one single lotus flower. The twist, the number of lotuses in this pond doubles every single day. Day 1, there's 1 lotus. Day 2, there are 2. Day 3, there are 4, and so on. Now, we know the pond is completely 100% full on day 30. So on what day was the pond exactly half full? Take a second and really test your intuition here. What's your gut telling you? Well, if your gut screamed day 15, you fell right into the linear thinking trap. The real answer is actually day 29. Why? Because if the amount of lotuses doubles every single day, then just one day prior to being completely full, it had to be exactly half full. Half doubled equals full. This just perfectly exposes how ridiculously fast exponential sequences scale right at the very end of their growth curve. It goes from half full to completely overflowing in a single day. Let's watch this explosive growth play out in another scenario, the king's treasure puzzle. So a king has 3 daughters. Each daughter gets 3 baskets, meaning 3 times 3 equals 9 baskets. Each of those 9 baskets has 3 keys inside, giving us 27 keys. Every key opens 3 rooms. Bam! 81 rooms. Each room has 3 tables, so 243 tables. Each table holds 3 necklaces, making 729 necklaces. And finally, each necklace has 3 diamonds. By multiplying by 3 7 consecutive times, we get 3 to the power of 7. The final haul? 2,187 diamonds. Step by step, layer by layer, just multiplying by the same number creates massive results. And apply it to something you probably interact with every day, a digital lock. Imagine a standard 5-digit lock. It has 5 empty slots.
Each of those slots can hold any digit from 0 to 9. That means you've got exactly 10 choices for the first spot, 10 for the second, 10 for the third, and so on. Based on that rule we literally just learned about combining choices, how many total possible passwords do you think exist for this lock?
To get the answer, we just multiply our 10 choices 5 times over. 10 times 10 times 10 times 10 times 10. Or if we're speaking exponents, that's 10 to the power of 5. And the result? A massive 100,000 possible passwords. This right here is exactly why digital locks and, computer encryption in general rely on exponents. The exponential math makes it incredibly difficult and tedious for anyone or even a fast computer to just guess the right combination.
Exponents are also super helpful when we're trying to grasp the sheer scale of massive numbers. Take the number 1 billion. It's a 1 followed by 9 zeros. We hear the word billion tossed around all the time, right? But our brains genuinely struggle to visualize what that actually means. So let's ground it in something we all understand: time. If we were to count every single second, exactly how long is 1 billion seconds? Take a wild guess at the real-world time equivalent.
Okay, let's break down the math. We know 1 minute has 60 seconds. 1 hour is 60 times 60, which is 3,600 seconds. 1 day is 24 times 3,600, giving us 86,400 seconds. To find the seconds in a year, we multiply 365 by 86,400 to get exactly 31,536,000 seconds per year. Now, for the punchline, if we divide our 1 billion seconds by the seconds in a single year, we land at approximately 31.7. Yep, 1 billion seconds is almost 32 years long. I mean, that is just a staggering reality check on how big a billion really is.
Mind-bending escalation phase here, and see how our brains utterly fail to perceive time at scale. Here's a question. How long is 1 million seconds compared to 1 billion seconds? To our human ears, million and billion sound so incredibly similar, right? They just sound like a lot. If I asked you right now to guess, mentally, the actual time difference between the two, what would you say? A few extra months? Maybe a year? Get ready, because the reality of adding those 3 extra zeros, which, remember, is multiplying by 1,000, is about to completely warp your sense of time. So, the crucial point is the staggering contrast. 1 million seconds is roughly 11.5 days. That's really not too hard to grasp. If you wait a million seconds, it's basically just over a week and a half. But 1 billion seconds? Guys, that is over 31.7 years. Think about that contrast for a second. The difference between a million and a billion isn't just a bit more. It's the difference between taking a quick 2-week vacation and working an entire human career. When you scale up exponentially by powers of 10, the math leaves our daily intuition completely in the dust. Finally, part 5, the rice and chessboard, the ultimate exponential legend.
Now, what's really interesting about this slide is how it tracks the absolute pinnacle of our exponential journey. The story goes that a clever mathematician asked his ruler for a very simple reward: 1 grain of rice on the first square of a chessboard, 2 on the second, 4 on the third, doubling all the way to the 64th square. Square 1 is just 1 grain. Square 2 is 2 grains. By square 10, it's 512 grains, so, a small handful. The ruler probably thought he was getting off super cheap, but let's follow the data down to square 64. By the time you reach the end of the board, the doubling results in over 18 quintillion grains of rice. To put that completely absurd number into perspective, 18 quintillion grains is enough rice to cover the entire landmass of the Earth several times over. It is a literal world-covering amount of food, and it all started from 1 single grain, simply because it doubled 63 times.
It's absolutely true. Exponents are the mathematical universe's hidden superpower. We've gone on quite the epic journey today. We started with folding a simple piece of paper and deciphering the deceptively slow start of a magical lotus pond. We upgraded our wardrobes, unlocked secret locker combinations, and learned that a billion seconds is an entire lifetime compared to just a million. And finally, we watched a single grain of rice bury a planet. So here is the big takeaway. Whenever you see things multiplying rather than just adding, pay attention. You are witnessing the most powerful force in numbers. I want to end our explainer today with a provocative question for you all. If you could apply the magic of exponential growth to just one skill in your life, what would you choose to multiply? Would you double your ability to learn a new language every week? Would you exponentially grow your patience, your creativity, or maybe your savings account? Think about how quickly that would change your entire world, just like the rice on that chessboard.
Thank you so much for joining me on this structured dive into the math that secretly runs our universe. Keep asking questions, keep looking for those hidden multipliers, and I will see you next time.